Okay, I have put on an Excel spreadsheet a data table for the investigation where we measured the absorbance versus concentration of red dye number 40, and then where you're supposed to use that information to create a Beer's Law plot and then uh, try to calculate the concentration of the unknown solution that was prepared from the 3.55 parts per million red dye stock solution. Um, and I'm going to just show you how to take that data and make your data table, uh, and then take that data table and format the graph of that Beer's Law curve. So once you have properly labeled your concentration, which was your independent variable, the part that was controlled by you, um, and the concentration unit, since there's so many units that you can measure concentration in, you have to identify that unit. And so I put all of these measurements here. These concentrations are in the unit parts per million. And then the instrument, the spectrophotometer, measured the absorbance value for each one of those at the analytical wavelength, the proper wavelength. Um, and it should have been, since this was a red solution, it should have been around 500 nanometers for the wavelength. The data, I started off here. This is the blank, pure distilled water, which we calibrated the instrument with and set that as 0. And then from that wavelength and that calibration, measured the highest absorbance for that concentration. So all you have to do is you select the data points that you have entered into your data table, and then you go to Insert Charts, and then I'm going to pick the scatter plot, and I'm going to pick the one with no lines on it. So this is my data. Your numbers may be a little different. Your concentrations probably will not, because you probably made the same concentrations that I did, because that was from the example. But if you didn't, that's fine too. You're going to put your concentrations and your absorbance values. Um, so when I do that, I get this graph, and it looks like from 0 parts per million to 3.5 ish parts per million, 3.55. I have, in that section at least of the Beer's Law curve, I have what looks like to be a linear function, which is pretty good. So just to label your graph, you need to do that. So a couple things. One, I might just call this title right here. I might just make that my chart title, and if I take that and copy it, I should be able to paste it. Just Control V. Oops. And paste it in there. And then I can start formatting the graph. So I'm going to bring this over just a little. I might actually even make it, just for a second, make it even like a little bit larger. Um, so you give your chart a title, uh, and then personally, you need to make sure you title each axis. So the part you controlled, or the independent variable, was the concentration of the standard solutions. So that's what you plotted on the x-axis. Um, so if I want to make chart titles, uh, you know, I can use Excel to do that. So I click on the graph, like right here, and then I can go to my Design tab, and I can add a chart element. So the axis titles, my horizontal axis right here, I'm going to call that the concentration. And then I need to put the unit in parentheses there, in parts per million, since there are so many different units for concentration. Um, And then I also want to title my vertical axis right here as absorbance. Now absorbance, you didn't have like a particular like a unit for that, so you can just put absorbance. It's just a value and with no unit indicated. So now another thing that I noticed is that all my measurements of absorbance on the instrument, all of them had 3 decimal places. So another thing that I'll look for you to do is to format the vertical axis where those things have 3 decimal places. So if you click on the axis itself there, and you can right click and go to format axis, and then you bring up this format axis tab here on the very first one. If you scroll all the way to the bottom, you may not be able to see it on mine, but at the bottom of that, when you scroll down, it says number. And then the number part that you can click from, it says category. And right now mine just says general. I'm going to change that to actually say number. And then I want to format the number of decimal places. And I want to change it. It says 2 right now. I'm going to format that as 3. And then just click enter, and it will change that to 3 decimal places right there. And then the second thing you can do to format the independent variables axis, the x-axis, is most of the concentrations that were prepared here have 2 decimal places. One of them had 3. That's just because you were limited to 3 significant figures based on the precision of the instruments and the concentration of the original stock solution, that precision. So, but you still format your x-axis, right? And then same thing, I'm going to go down to the format axis, scroll all the way down to number, and change it from general to number and 2 decimal places. Now it'll say that, and then I just press enter, and I can close that for just a second. So now you're looking at a graph that looks like this, and you'll notice you have some grid lines there. Personally, I don't like grid lines on that graph. I'd just rather look at just the data points. Now, when you want to add a trend line to this. So you're going to click on the points, actually right click, and it says format or add trend line. So you click add trend line, and then the first thing you want to do is make sure that you select linear. Then at the bottom, you may not be able to see it on my screen, but at the bottom of that format trend line section, after you click linear up here, it's got a couple of things. You want to do 3 things. You want to click where it says set intercept at 0. So set intercept and make sure it says 0. Display the equation and the correlation coefficient R squared on there. So now you have that equation for your graph. So here I have y equals 0.3738x, and that's R squared value. That is pretty much then it's telling me that's a perfectly correlated set of data points that all fall on the line, which is pretty remarkable for me there, for that that set of data. But that's as good as you can get. It's +1 for a positively sloped line. If it was going the other direction but it was perfect, it would have been -1. So this shows as concentration of the solution increases, the absorbance increases, and it increases in this way right here. So This is the equation that describes that increase. The only thing I want you to do with that is, instead of saying just Y, I want you to actually say absorbance. You can just put ABS. And then for X, instead of just having X there, put parentheses concentration. And you can just put CONC. So the absorbance is equal to 0.3738 times the concentration. That part, gives me the equation that I can use to solve for the unknown's concentration, because I did measure the unknown's absorbance value. So now I have an equation for the line of best fit, and I can use that to do calculations with. The next thing is I will take this equation right here, and I'll use that as to calculate the concentration of the unknown. Let's see, looking at my notebook, the unknown's absorbance was, looks like 0.148. So that was my unknown absorbance. When I measured the absorbance of the unknown on the same instrument, the same way. Okay, and so now that I have the unknown absorbance, this equation right here, I can use that to solve for the concentration. So the slope from that is 0.3738. I can solve for the concentration of unknown, and that would be in units of parts per million. If you look at your equation, if you have the absorbance and you divide it by the slope, then that'll give you your concentration. So the absorbance was 0.148, the slope is 0.3738. If I divide that, then I should get the concentration experimentally for that. So in here I can just let the Excel calculate that, equals that cell divided by slope, enter. And then that's too many significant figures, obviously. I'm limited to 3, so I'm going to back that down with my decrease decimal button until I get to 3 significant figures. Okay, so that's my experimental concentration. Now the actual concentration, I'll tell you here in this, it's also in parts per million. That a little wider so we can. The actual concentration is 0.405 parts per million. So that's when I made the solution, that's what its concentration was. From that, I can calculate a percent error. Now remember that percent error is the absolute value of the error, or the difference in the two, divided by the actual times 100. So the way you would type this in Excel and let Excel calculate that would be in that cell right beside that, click in the cell, type an equals mark, and then the first thing is just take absolute value of the two things, this minus that. Okay, and whatever that is gets divided by the actual concentration, and then times 100. And then I can reduce the decimal. When you subtract these two, that's where your sig figs are going to come from. So when you subtract the numbers 0.405 minus 0.396, you get 0.009. That's only one significant figure. So that would mean you have to go by your subtraction. So when I subtract those, the error value between the two is 0.009. The percent error has to be reported as 2%. Just like that. So from my data, I entered it in here into Excel. I got the Beer's Law curve, and then I got my unknowns absorbance, and I used the slope from the equation, and then I used that for calculate the concentration, and then compare that to the actual concentration for the red dye in the unknown, and then I calculated percent error to quantify that just a little bit. Just say, hey, this is what the experimental result was. This is what was revealed as the actual concentration. This is the percent error between the two. So part of this, I'll show you in another video how to, once you've made this, you want to insert this information into your lab report in the data in the results section. So anyway, this will get you to be able to format your graph the way that I'd like to see it, and then from there we'll talk about putting it into your lab report.